All right, today we're going to tackle one of the absolute legends in the world of computer science, the Quicksort algorithm. Think about it. When performance really matters, like when you're digging through massive databases or trying to handle millions of user records, the way you sort your data makes all the difference. It's the line between a system that feels super snappy and one that just crawls. So, what's the secret sauce? What actually makes Quicksort so quick? And maybe more importantly, what's its hidden weakness? Yeah, that's what we're digging into. Quicksort is famous for its speed, but it has this one fascinating and potentially catastrophic flaw. We're going to uncover both its genius and its Achilles heel. Okay, so what is Quicksort? Well, at its heart, it's a really beautiful example of a strategy called divide and conquer. And that's a super powerful idea in computer science. You just take a huge, messy problem, break it down into smaller, more manageable pieces, solve those, and then stitch the results back together. And the logic is actually pretty straightforward. First, you just pick any element from your list. We'll call that the pivot. Then you shuffle everything else around, so all the items smaller than the pivot are on one side, and all the items bigger are on the other. And then you just do that exact same process again on those two new smaller groups. That's it.
To really get this, let's just forget all the technical jargon for a minute. Let's imagine a factory full of robots, and they all need to line up by height, from shortest to tallest.
So the manager comes up with a clever plan. First, a pivot bot gets picked and stands in the middle. All the other robots look at it. If you're shorter, you go to the left. If you're taller, you go to the right. Now we have two new groups. And guess what? Each of those groups does the exact same thing. This just keeps going until every group is down to just a single robot. And because of how they were divided up, when you put it all back together, voila, the entire line of robots is perfectly sorted. This whole process of rearranging everything around the pivot, well, it has a name. It's called partitioning. And this is the engine that makes the whole Quicksort algorithm go. After you partition just once, that pivot element is now sitting in its final, correct, sorted position. It will never have to move again. Now, here's something interesting. Quicksort isn't really one single rigid algorithm. It's more like a family of algorithms that all use this same pivot and partition idea. The two most famous versions you'll hear about are the Lomuto and Hoare schemes, named after the computer scientists who came up with them. And they actually work pretty differently. The Lomuto scheme is a bit easier to wrap your head around. It just scans from one end. The Hoare scheme is kind of clever. It scans from both ends at the same time, moving in towards the middle. It's definitely more complex, but that complexity pays off. Hoare's method ends up being way more efficient, doing about 3 times fewer swaps on average, which makes it a lot faster in practice. Okay, we've seen why it's great, but now let's talk about the dark side. The entire efficiency of Quicksort, everything, hangs on one single choice: picking the pivot. If you pick a good pivot, you split the list nicely in half. But if you pick a bad pivot, well, that's when things go horribly wrong. So let's run a little thought experiment. What happens if you try to use Quicksort on a list that's already perfectly sorted? And let's say our algorithm is kind of naive and always just picks the very first item to be the pivot. What do you think would happen? It's a disaster. The partition becomes totally unbalanced. Since the pivot is the smallest thing in the list, everything else is larger than it. So you end up with one group that's completely empty and another group that has, well, basically the entire rest of the list. We've done all that work and we've barely made the problem any smaller. And if this bad choice keeps happening over and over, the algorithm's performance just craters. It degrades to O of n squared, or quadratic time. That means if you double the size of your list, the time it takes to sort doesn't just double, it quadruples. To put that in perspective, it becomes as slow as something like bubble sort. Suddenly, our Quicksort is anything but. So that's the big question, right? How do we stop this from happening? Well, thankfully, some very smart people have come up with clever strategies to make sure we almost always pick a good pivot and avoid this worst-case scenario. Okay, so just picking the first or last element is simple, but as we just saw, it's risky. A much better idea is to just pick an element at random. I mean, the chances of you randomly picking the worst possible pivot every single time are astronomically low. But one of the most popular and robust strategies is something called median of 3. And this is a really brilliant compromise. Instead of just grabbing one element, you look at 3 of them: the first one, the one in the dead center, and the very last one. Then you just pick whichever of those 3 is the median value, and that becomes your pivot.
It's a simple little check, but it makes the algorithm way more resistant to those common problem cases, like data that's already sorted.
You can see here in this pseudocode how that randomization actually works. The key idea is super simple. Before you even start partitioning, you just pick a random element from anywhere in the array and swap it with, say, the last element. By using this random element as the pivot, you pretty much guarantee that on average your partitions are going to be reasonably balanced, and you sidestep that whole worst-case nightmare.
So we've seen its big weakness, and we know how to fix it. But that still begs the question, why is Quicksort so dominant in the real world? Well, it all comes down to a few key advantages it has in practical, everyday performance. Its real-world speed isn't just about great math on paper. Two other factors are just as important. One, it's an in-place algorithm, and two, it has excellent cache locality. Now, cache locality is just a fancy way of saying that the algorithm accesses computer memory in a very predictable way. Modern hardware loves that, and it can speed things up, giving Quicksort a real physical edge. And that other point, being in place, is a massive deal. It means Quicksort does all its work right there within the original array, just shuffling things around. It doesn't need to create a whole separate copy of your data. This is a huge advantage over an algorithm like MergeSort, which needs a ton of extra memory, especially when you're working with gigantic data sets.
Yeah, this table really puts it all into perspective, doesn't it? I mean, just look at Quicksort compared to the others. Sure, MergeSort matches its average speed, but look at that extra space it needs. And the simpler sorts, they just get left in the dust. Quicksort hits that perfect sweet spot of fantastic average speed with almost no memory overhead.
When you boil it all down, Quicksort is just a masterclass in algorithmic trade-offs. It sacrifices that absolute guarantee of good performance in the worst case for superior, blazing fast speed in almost every single real-world scenario. So that leaves us with a final question to chew on. If you were designing a system from scratch, what would you choose? The safety of guaranteed performance or the thrill of blistering real-world speed?